Good morning dear students, I am your physics professor Dr. Nagaraj. So I am here to explain Maxwell's equations and electromagnetic waves. This is second video on this particular chapter. It is actually module 4 of engineering physics for triple E stream. Anyway, in the previous video we have discussed about scalar field, del operator, divergence, curl and gradient, and also we have derived one equation that is nothing but Gauss divergence theorem. Let me proceed further. I just repeat Gauss divergence theorem. Actually, Gauss divergence theorem helps us to go from surface integral to volume integral. What it says, surface integral of flux of a vector, that is E dot ds, is equal to, see when I write ds it is surface integral, is equal to volume integral of divergence of the vector, that means dv. So when I write dv it is volume integral. And we proved this in the previous video. This is divergence theorem. Gauss divergence theorem is one of the expected question. It is there in the syllabus. But there is one more theorem called Stokes theorem. This is divergence theorem. Next one is Stokes theorem. Stokes theorem only statement, no derivation. What actually Stokes theorem says? Stokes theorem helps us to convert line integral into surface integral. See dear students, here we go from surface to volume, whereas in Stokes we go from line integration to surface integration. Now comes the statement, according to Stokes, line integral. Sir, why are you putting the circle? You can write only simply integration symbol. This question might have arisen in your mind. See, simply if I put the integral, it is normal integration, means it is only one dimensional integration. When I put circle here, it may be line integration or surface integration or volume integration. Strictly speaking, for line integration there will be only one integral sign, whereas for surface integration they put two integral signs, for volume integration they put three integral signs. But here, just for the sake of clarity, I am not putting three integral symbols, only one integration symbol. Well, now comes the Stokes theorem statement, line integral of a vector, see dear students, I am writing dl, is equal to surface integral of curl of the same vector. See, this is curl, and when I say surface integration I must write ds. This is Stokes theorem. So divergence theorem takes you from surface to volume, whereas the Stokes theorem takes you from line to surface. Having said this, now let us proceed further with the Maxwell's equations discussion. Dear students, as I told in my previous video, Maxwell's equations are most important achievement of the 19th century. Maxwell did not make any new assumptions, did not write equations on his own. Actually, he made use of vector calculus and reframed four statements which are already known to you. And those four statements, when he reframed, he got four equations which are now I am calling as Maxwell's equations. Sir, you said four statements are already known to us. Can you tell us which are those four statements? Yes, I will come to that now. First one, dear students, you might have heard of Gauss theorem. Which Gauss theorem? Not Gauss divergence theorem, Gauss theorem in electrostatics. Yes sir, we know Gauss theorem in electrostatics. Please recall from PUC, what Gauss theorem in electrostatics says? Total flux over a closed surface is equal to 1 by epsilon naught times charge enclosed by the surface. This is Gauss theorem statement. Gauss theorem finally leads to one equation which I am calling as Maxwell's equation number 1. Dear students, in the syllabus, derivation not mentioned, only equation we have to write. And Maxwell's equations we can write in two different forms. Number one, it is in differentiation form or differential form. That means in terms of del we can write. Also we can write in terms of integral form. So there are two forms of Maxwell's equations, but in the syllabus only differential form is mentioned. So I go with only differential form. Yes, having said this, now I proceed. using Gauss divergence theorem, using Gauss theorem in electrostatics, we can show that del dot epsilon E is equal to rho suffix V. How, sir? No, you need not have to worry at all. Nobody will ask you derive this equation. This is just taken for granted, and this is my Maxwell equation number 1. I write it like this. So according to Gauss theorem, total flux is equal to 1 by epsilon naught times the charge enclosed. This can be reduced to this form, and I write once again this as del dot D, that is equal to rho V. Dear students, whenever you write del, remember there must be an arrow mark on the top of it. So del is a vector, E is a vector, epsilon is not a vector, of course, it is nothing but permittivity. They are all well known factors in fact. Well, del dot D is equal to rho V. Sir, what is rho V? Rho suffix V stands for volume charge density. You know, there are 3 types of charge densities on the line. PUC, once again PUC, straight conductor, it will be having charges on it. It is linear charge density. Okay, so in a straight conductor, we have charge distribution over the entire length. We have linear charge density lambda. Whereas in case of sheet, we have surface charge density, that is sigma. Whereas in case of sphere, we have volume charge density, that is rho suffix V. Okay, so that rho V I am using here. Well, this is equation number 1. Well, D is also a vector because E is vector, D is vector, and D is called as displacement vector. It is not that displacement in equations of motion. It is totally different. Here it carries totally different meaning, but no need of worrying much about this D. Just take it for granted D is equal to epsilon E. So this is equation number 1. This is my first equation, that is Maxwell's equation. So for Maxwell's equation, origin is Gauss theorem in electrostatics. Okay, dear students, now comes the second one, second statement. I told you know 4 statements. From those 4 statements, Maxwell wrote 4 equations. One statement gone, that is Gauss theorem. Second statement for second equation. Once again it is Gauss theorem only. Please recall magnets, bar magnet in matter and magnetism chapter in the previous year, that is in PUC, you might have studied Gauss theorem. What Gauss theorem says in magnetism? If there is a bar magnet, it is associated with magnetic lines. They diverge from the north pole, converge at the south pole, and inside they form a closed loop. You can have many number of lines like this. They all are forming the closed loop. If you now imagine a closed boundary over any region, if you consider Gaussian surface, according to Gauss theorem, flux is equal to 0. See, in electrostatics, flux is equal to 1 by epsilon naught times charge enclosed. Whereas in magnetism, flux is equal to 0. This is Gauss theorem in magnetism. And once again, using this equation, we can prove that del dot B is equal to 0. This is my second equation, Maxwell's equation number 2. So first equation is from Gauss theorem electrostatics. Second equation is from Gauss theorem magnetism. Are you following? Yes, I think you are following. So you need not have to worry about how these equations are derived. Ad bekagilla, not necessary. Nobody will ask you to derive Maxwell's equation. They only will ask you to list the Maxwell's equation. Give Maxwell's equations, no derivation. Well, first part is over. 2 equations I have written. Coming to third part. Third equation is based on third statement. Which statement do you know? Yes, it is electromagnetic induction chapter. In PUC, you have studied electromagnetic induction, Faraday's laws of electromagnetic induction. There Faraday says, in a coil, please recall, in a coil, EMF is induced due to rate of change of magnetic flux. Whenever magnetic flux changes, EMF is induced. That induced EMF is against the cause. That means according to Lenz's law, EMF is opposing the cause. All put together, we can write one equation. Induced EMF is equal to minus d phi by dt. This is Faraday's law of electromagnetic induction. Of course, I have one proportionality constant N, but that is not required here. So E is equal to minus d phi by dt, where minus sign indicates that induced EMF is against the change in the flux. Okay, na? This is Faraday's law of electromagnetic induction. Now using this statement, this is nothing but Stokes theorem. Okay, Gauss theorem helped us to obtain equation number 1 and 2. Now Stokes theorem will assist us to derive next equation, that is del cross E is equal to minus dou B divided by dou T, where E stands for electric field, B for magnetic field. Dear students, EMF associated with electric field, flux associated with magnetic field. Once again I am repeating, derivation not necessary. And of course you have to put arrow mark wherever you have the vector quantity. Well, this is nothing but equation number 3. I write it as equation number 3. 1 over 2 over 3 over. Shall I continue? Okay. So third equation is ready. Now comes the fourth equation. Before coming to fourth equation, let me talk little bit about Ampere-Circuital theorem. This you have already studied in PUC. I just repeat it and then I write the fourth equation here itself. Now comes Ampere-Circuital theorem. What Ampere-Circuital theorem says? If there is current in a region, imagine a boundary around this current, that is called Amperian loop. Draw tangent to the Amperian loop, it represents magnetic field. Then according to Ampere-Circuital theorem, the line integral of B dot dl is equal to mu naught times current enclosed by the loop. It is like total flux is equal to 1 by epsilon naught times charge. Here total flux only, but it is not B dot ds, it is B dot dl is equal to mu naught times I. This is called Ampere-Circuital theorem. Okay, this also you studied in PU. Well, we have one relation between B and H. Put B is equal to mu naught into H. Therefore, this equation becomes mu naught H into dl is equal to mu naught I. Cancel mu naught on both the sides, then it is integral of H dot dl is equal to I. So, this is mathematical form of Ampere-Circuital theorem. Even this also, right? Well, we have one serious problem here. According to this formula, whenever there is current, there will be magnetic field, or conversely, wherever there is magnetic field, there must be current. This seems to be okay if there is a straight conductor. If there is a straight conductor carrying current, there will be magnetic field. Suppose if you have a capacitor, well, we have a capacitor and then you connect this to AC source, we have a current flowing in the circuit. Now the question, there is no connection here. How come current flowing in the circuit? If I imagine a boundary over here, does it mean that there is no current, so there is no magnetic field? This also you studied in PUC. See what I mean to say, between the two plates there is no continuity. So literally speaking, there is no current here. But actually, when you take the Amperian loop like this and measure, you will have magnetic field. Here is a contradiction. There is magnetic field, but there is no current. But what I said, whenever there is magnetic field, there must be current. Okay. So in order to overcome this difficulty, overcome this contradiction, Maxwell introduced one new type of current, that is called displacement current. Maxwell said, between the two plates, there is no traditional current, means there is no flow of charge, but still there exists a current called displacement current. I will explain it later on. So using displacement current, Maxwell modified this formula, and that formula is integral of H dot dl is equal to I plus ID. Dear students, this is called Ampere-Circuital theorem. This is called Maxwell-Ampere circuital theorem, modified theorem. What is that modification? The introduction of displacement current. Introduction of displacement current. Are you following? What is displacement current? I will tell you later on. See, displacement current is one of the important parameters introduced by Maxwell. And from this equation, we can comfortably write fourth Maxwell formula. So, fourth Maxwell's equation is del cross H is equal to J, or del cross H is equal to J plus epsilon dou E by dou T. There are two equations, right? Either this or this. What is the difference? I tell you later on. So this is equation number 4. Just watch here. This is equation number 1. This is equation number 2. This is equation number 3. This is equation number 4. All 4 equations are ready. And these equations are based on 4 statements. First equation is obtained from Gauss theorem. Second equation is also obtained from Gauss theorem, but in magnetism. Third equation is obtained from Faraday's law. Third equation is from Faraday's law. Fourth equation is from Ampere-Maxwell circuital theorem. Ampere-Maxwell circuital theorem finally leads to this. Okay, sir, you wrote 2 equations here. Which one to consider? Actually, I go with this one only, del cross H, if the space is vacuum. If the space is not vacuum, if you are talking in a given medium, air medium or some liquid medium or some gaseous medium, then this extra term will come. This extra term will come. Okay, na? So, del cross H is equal to J plus epsilon into so much is the equation, fourth equation in medium. This is the fourth equation in free space or vacuum. Having said this, now Maxwell's equations are ready. So if you are asked to write Maxwell's equation, dear students, please write like this. 4 Maxwell's equations are based upon 4 statements. Number 1, Gauss theorem. Better you define Gauss theorem and then write the equation. And whenever you write the equation, it is a foremost duty to explain the terms. What is D, what is rho, all those things you have to define. Next, second equation is also from Gauss theorem but in magnetism. According to Gauss theorem in magnetism, total flux is 0, and using this we can show that del dot B equal to 0. Nobody will ask you to show. Better you write like that. We can show that. Next, third equation is from Faraday's laws of electromagnetic induction, and fourth equation is from what? Ampere-Maxwell circuital theorem. So this one only you write, this one only you write. Then why did you write this one, sir? Because I need this equation in one of the derivation which I am going to do afterwards. Okay, na? Well, that's all about Maxwell's equations. Now comes, okay, suppose if you want to put them in wordings ಅಲ್ಲಿ ಬರೆಯೋದಾದ್ರೆ, you can put it like this. Divergence of a displacement vector is equal to charge density, volume charge density. Divergence of magnetic field is equal to 0. Curl of an electric field is equal to negative rate of change of magnetic field. Curl, see, in 2 cases it is divergence, in 2 cases it is curl. Next, curl of the magnetic field is equal to current density. J is current density. Okay, na? Well, that's all. Now I move on to displacement current. The next heading is displacement current. What is displacement current? Before defining displacement current, I will do one derivation. That means expression for displacement current. This is slightly different approach. Normally teachers, what they do, they will give definition, then they will give some properties, then they will take up the differentiation. But I go in reverse manner. I think this is going to be more convincing. Well, I take up the derivation part. The derivation goes like this. Same parallel plate capacitor. I have 2 plates separated by some distance, okay, and connected to AC source, of course. Well, in PU, you already studied about the electric field existing between the 2 plates. What is the electric field between the 2 plates? We know it is nothing but sigma divided by epsilon naught, assuming that there is no dielectric medium, only free space. Okay, na? What is sigma here? Sigma is nothing but charge divided by area. charge divided by surface area. You can either write A or you can even write Q divided by ds also, where ds is nothing but area of this plate, okay na? Well, that I substitute. E is equal to Q divided by ds into epsilon naught. Well, take ds this side, it becomes E ds is equal to Q divided by epsilon naught. Okay, dear students, come and tell me, what is this EDS? What is this EDS? It is nothing but flux. Somewhere here I have written EDS is nothing but flux, electric flux. So phi is equal to Q divided by epsilon naught. Okay na? Sir, this is nothing but Gauss theorem, sir. Yes, you are 100% correct. Q is nothing but 1 by epsilon naught into, sorry, phi is nothing but 1 by epsilon naught into Q. Adanne, once again I have written here, that's all. See, equations are very important. You can play with equations, okay, and they will give you a sort of pleasure, right? Now you differentiate this. Differentiate d phi by dt is equal to 1 by epsilon naught into dq divided by dt. Correct? Take epsilon naught here. Epsilon naught into d phi by dt is equal to dq by dt. dq by dt. Please follow carefully, dear students. What is dq by dt? In PU, your teacher might have told you dq by dt is nothing but rate of change of charge, rate of flow of charge. Yes, rate of flow of charge represents what? Sir, it is current. So if RHS is current, LHS must be current. RHS is current, then LHS must be current. Yes, you are correct. This is current. That means this current I write as, okay, now I write it as I suffix d is equal to epsilon naught into d phi by dt. This is the expression for displacement current. Now from this you can define displacement current. Dear students, ordinary current is nothing but rate of flow of charge. If the charge is flowing, the number is changing, then it gives you normal current, which is called traditional current, conventional current, etc. If there is change in the flux, that also gives current. That is the meaning of this equation, and that current is called displacement current. Now comes the definition. So that's what I said. First I do the derivation, then I give you the definition. But while writing, you start from the definition only, because now you know what is displacement current. So what is displacement current? It is a current arising due to rate of change of electric flux. Please remember, it is not magnetic flux. Rate of change of magnetic flux gives you EMF. Rate of change of magnetic flux gives you EMF. Rate of change of electric flux gives you current. That is called displacement current. Okay, and it is given by epsilon naught into d phi by dt. Okay, this is the displacement current. Now some differences between displacement current and ordinary current. First, ordinary current is due to rate of change of charge. Displacement current is due to rate of change of flux. Okay, ordinary current is associated with the charge, and for the flow of charge I need wire, material, medium. So current, that is ordinary current, exists only when there is material wire. Medium must be there, and that medium also should assist for the flow of charges. Whereas flux can exist in the vacuum. Between the two plates there are electric lines. Electric lines are there, means flux is there. Flux exists even in free space also. Therefore displacement current exists in free space. That is what Maxwell assumed here. While giving this equation, he assumed that in this region there is some current. That current does not require any medium for the flow, and that current is displacement current. What all it requires? It requires change in the flux. Which flux? Electric flux. Magnetic flux change gives you totally different phenomena. This is displacement current. So second difference, displacement current does not require any medium, whereas a normal current requires medium for the propagation. Okay, and finally Displacement current exists even in vacuum also, whereas ordinary current does not exist in vacuum. So these are the three differences, and rest of the things like unit of displacement current is also ampere. Displacement current can produce all the effects produced by normal current. Other things are as it is. So I repeat, displacement current is a result of change in the electric flux. Displacement current does not require any medium for the material medium for the flow, and displacement current can exist even in vacuum. Okay, dear students, now with this I take up another statement, that is equation of continuity. Equation of continuity. What is equation of continuity? That I will explain now. See, some parameters are depending on some other parameters. So one physical quantity or one quantity depends on other quantity. Something depends on some other things. If that is changing, this also should change. If that is not changing, this should not change. Then we can say between them there is a continuity. For example, hungry. I am hungry. So I am not taken anything from morning, so now it is 8 p.m. I am hungry. I want to eat something. Okay, hungry depends upon food, what is there in front of me on my dining table. In plate I have roti, chapati, or rice, or fruits, or milk, something like that. All are eatables. Okay, so if I consume those eatables, my hungry will decrease, right? So I get satisfied. As I consume, the amount available in the plate decreases, and at the same time my hunger level also decreases. So that is changing, even this is also changing. This type of connection must be there. Then only I can say my hungry and the food items in my dining table, my plate, both are continuous. They have the continuity relation. This is one vague example I have given. Coming to physics. Dear students, current, as you all know, depends upon the charge. If charge changes, current also changes. So current is something like hunger, charge is something like food. Okay, when charge changes, current also changes. Therefore, the equation connecting them is nothing but continuity equation. So I is equal to dq by dt is a continuity equation. Okay, like that I will write one more equation which is also called as continuity equation, that is J is equal to minus dou rho v divided by dou t. This is actually called as a continuity equation. What actually this is? First of all, what do you mean by continuity? Something is said to be continuous if a parameter depends on other parameter, and when those parameters change continuously, this parameter also should change. If you are confused, you can write like this. Something is said to be continuous if A depends on B such a way that whenever B changes, A also should change. Whenever charge changes, current also should change. Okay, now coming to this J rho V. See dear students, J stands for current density. Current density is nothing but some current which is flowing across a cross-sectional area. Current flow per unit area, how much current it is flowing. Well, current, as you all know, is nothing but flow of charge. Okay, suppose the charge is coming, more charge is coming from the volume. That means change in the volume charge density per time. More charges are coming, like water is coming from the pipe, or you have water over there, it is coming out, right? So how much of water is coming? That I am measuring. Suppose if more water is coming out, then I can measure more here. Less water is coming, I measure less here. So whatever the change occurs, my measurement also correspondingly will change. Like in my dish plate, I have a lot of eatables. Okay, so accordingly my hunger level also get reduced. But suppose if I am too much hungry, only one peanut is there, or only one roti is there, only a little little bit of rice is there, what is the use, right? My hunger level will not reduce. Like that, even here also, if more item is coming, means more charge is coming from a point, then my measurement, that is current density, will be more. Current density will be more. Okay, it is something like this. Let us say from the classroom, students are coming out. Let us say in the classroom there were 100 students, maybe some auditorium. So I am standing at the gate and counting the students. So I am counting in every 1 second. Every 1 second, if there are more number of students, more will come. So 10 students, 20, 30, 40, like that they will come. Okay. So dou rho v by dou t more, j also more. Correct? It is understood. So that is one thing. But what is this negative sign, sir? Why you have negative sign there? Here is the beauty of the equation. Listen carefully. Students are coming out from the auditorium. Water is coming out from the enclosure. Food is getting into my stomach from the plate. Plate is the source. That water bowl is the source. Auditorium is the source. Food item is the charge. Okay, students are charged. So students are coming out from the room. Now tell me what happens to number of students present in the room. Whether it keeps on increasing or decreasing or remains same. Anything can happen. It can increase, it can decrease, it can be same also, provided when depending upon the inflow. Suppose if our auditorium has got another door that side. Okay, from that side students are entering, this side students are leaving. Number of students entering is equal to number of students leaving, no change. If more students are entering, then there will be increase in the number. If less students are coming, there will be decrease in the number. If no students are entering, definitely there will be decrease in the number. Here, plate. If the plate is already containing some food items, no further supply, then there will be decrease in the food item. And you have water coming out, there is no inlet, then water in that region keeps on decreasing. Like that, in a particular region, charge is coming out. More and more charge coming out means in that region, amount of charge is decreasing. That is represented by negative sign. So this equation tells you about what you are measuring, what is coming, what is happening there. Three things you are getting here. What is you are measuring? Current density. What is coming out? Charge per unit volume. And what is changing over there? Charge density is changing. Rho v is changing, means it is decreasing. This is called equation of continuity. Actually, it appears to be very simple, but it has got lot of meaning, and it is going to play a lot of role in electromagnetics in subsequent discussions. Well, that's all about equation of continuity and equation of continuity. Okay, maybe it may appear along with one major question. What is equation of continuity? Or write the equation of continuity and discuss it. Okay, this you write and write down. According to this equation, J is current density. It increases when the dou rho v by dou t increases. But negative sign indicates that when more charges are coming out from the given enclosure, inside the enclosure, amount of the charge decreases. That is the meaning. Okay, see, negative sign has got different meanings in different contexts. Here negative sign is standing for totally different reason. Here negative sign represents that EMF is opposite to the change in the flux. Here negative sign represents that when more charges are coming out inside the region, magnitude of the charge is reducing, like that. Well, I see this time is very limited, otherwise I would have explained it in a beautiful manner. Okay, since your examinations are fast approaching, I am just giving only the surface explanation, and of course detailed explanation is not required because derivations and other things are not there. In fact, we can derive this equation from the basic principles. Well, so far I explained the Maxwell's equations and also equation of continuity and then displacement current. Now it is time to derive an equation for electromagnetic wave. This is another important question in this chapter. So set up two-dimensional or second order differential equation for electromagnetic wave, or obtain the second order differential equation for electromagnetic wave in terms of electric field. According to Maxwell, whenever electric and magnetic field vibrate perpendicular to each other, there will be a wave produced and propagating in another direction. This wave is a combination of electric field and magnetic field, and that wave is nothing but electromagnetic wave. So now we have to derive the expression for electromagnetic wave. I make use of almost all the Maxwell's equations. So therefore, I retain Maxwell's equations and continue the derivation over here, right? This derivation is bit lengthy, so follow carefully. Straight away I can start, and even you also can start like this. We know that I make use of this equation first. Del cross E is equal to minus dou B divided by dou T. So you write like this. We know that. Okay, step by step I will explain. Next, put B is equal to mu into H. This I already mentioned while discussing Ampere's circuital theorem. Okay. Therefore, this equation becomes, it is del cross E is equal to minus mu, I will write first because it is constant, into dou by dou T of H. In the place of B, I should have written mu H. Mu is outside. Okay. Now you take curl on both the sides. That means already I have del cross E. Multiply this once again by del, cross multiply. Okay. Del cross E is equal to minus mu into dou by dou T of del cross H. Are you following? Call this as equation 1. Del cross H. Right. Now comes one new equation which we have not discussed so far. That you have to remember. We know that. Please remember, though actually we don't know right now, but you sometimes it happens. You have to write like this only. So we know that del cross E is equal to del of del dot E minus del square E del square E, right, like this. This is one equation which you are supposed to remember. Well, now I make use of this. So equation 1 becomes, what will happen to my equation 1? I write it here, del cross E, that is del of del dot E minus del square E is equal to minus mu del dou by dou T of del cross H. Okay, del cross H, right. Next, coming to, okay, I will call this as equation number 2. We know that del dot epsilon E is equal to rho V. That is my equation 1, Maxwell's equation 1. Therefore, del dot E is equal to rho V divided by epsilon. Call this as equation number 4. Okay, na? Next, also we know del cross H is equal to this. Yes, this I make use of. J plus epsilon dou E divided by dou T. I call it as equation 5. See, dear students, first I started with Maxwell's equation number 3. Now I am making use of Maxwell's equation number 1 and equation number 4. Except second one, I am making use of all. First one, third one, fourth one. Okay, I repeat, first I consider del cross E, that is minus dou B by dou T. B I replace. Then I got this equation. Then I take curl on both the sides. Del cross E. Curl of a curl is equal to so much. This one you have to remember. Somehow please remember. Then this I substitute in the equation 1. So I have this equation number 2. Now del dot E I replace. Del cross H I would like to replace. Well, del dot E I have from equation number 1. Del cross H I have equation number 4. Correct? Okay, dear students, let us go ahead. Well, substitute equation 4 and 5 in equation 2. equation 2, what we will get? Del dot E, that is del of del dot E, that is rho V divided by epsilon, minus del square E as it is equal to minus mu dou by dou T of del cross H is already available, J plus epsilon dou E by dou T. I hope you are following. Proceed further. In vacuum or free space, remember rho V equal to 0, J equal to 0. In vacuum there is no charge, therefore there is no charge density. Therefore first term becomes 0, rho V 0 minus del square E is equal to, here first term becomes 0, I have minus mu into mu into epsilon is also there, dou square E divided by dou T square. Understood? One step I am missing here or skipping here. I should have written this as 0, this as 0, but I hope you are able to manage. Now you cancel minus on both the sides, then you left with del square E is equal to, in vacuum mu is mu naught, epsilon is epsilon naught, mu is mu naught, epsilon is epsilon naught. Therefore mu naught epsilon naught dou square E by dou T square. Actually this is very much similar to a progressive wave. A wave which is propagating with certain velocity is given by this equation only. This we derive in mechanics. That is del square F is equal to 1 by V square into dou square F divided by dou T square. Okay, or sometimes we write this as one dimension. No, for one dimension you can write this as dou square F divided by dou X square is equal to 1 by V square into so much. This is actually wave equation. So it is exactly similar. Therefore we can write 1 by V square is equal to mu naught epsilon naught. Since velocity of the light is represented by c, I rewrite this as 1 by c square is equal to mu naught epsilon naught, athwa c is equal to 1 divided by mu naught epsilon naught, that is speed of light. So question will be like this: derive second order differential equation for a progressive wave in terms of electric field. See, I finally got equation in electric field, and also derive the expression for speed of the light. C is equal to 1 by root of mu naught epsilon naught. Here is the derivation. Mu naught is nothing but 4 pi into 10 power minus 7. Epsilon naught is nothing but 8.85 into 10 power minus 12. Dear students, see, here is an interesting thing. Maxwell was not sure of this derivation. He had assumed that whenever electric field and magnetic field vibrate, wave is produced. That wave is a light wave. That wave is an electromagnetic wave. If it were to be electromagnetic wave, it should travel with speed of 3 into 10 power 8 meter per second. So he substituted mu naught and epsilon naught value. For his surprise, he got it as 3 into 10 power 8. That is the beauty of science. That is the beauty of Maxwell's equation. That is ultimate. So he just gave a thought and he worked on it. See, that's what I am telling you. Your thoughts must be proper. The direction in which you proceed must be proper. Definitely you will reach the destiny. So, but your thoughts must be proper. Whether it is thoughts in the subject study, thoughts in your life, or thoughts about whatever you do, it must be proper, and the approach also must be proper. Maxwell is the best example. We must salute Maxwell for his wonderful achievement. Okay, this is the equation, and here whenever there is electric field and magnetic field vibrating perpendicular to each other, say for example electric field is vibrating in this direction and magnetic field is vibrating in this direction, and then electromagnetic wave is generated and propagating in this direction. Well, electric field is along say y axis, magnetic field is along z axis, wave is propagating along x axis. So we can write electric field component, also magnetic field component. All those details are available in my notes. The description box contains the link. Please click the link and download the notes. And also, if possible, I will share the numericals video. Okay, but even in the material numericals are solved, please go through it. it. Well, with this I am going to stop this video. Remaining part of this chapter like polarization, properties of waves, all those things are self-explanatory. I have given notes in a detailed manner. Please go through it. Well, thank you very much for your cooperation, dear students. Wish you all the best. Do well in the exams. Okay, thank you once again.